Good? No? Sorry. Okay. So, well, you get to come back here and so you survived. Not bad. One of my close friends is the general manager of Keller's, Magic and Comedy Club in here. And he got me free tickets for the show this past weekend, which he does every once in a while, which is awesome. It's nice to know people. And I got to see a comedian juggler. He's on Netflix. He's like well-known. He did some amazing stuff. He balanced a leg, and he juggled on a unicycle while balancing a spinning ball. I couldn't.
What kind of noise is behind
a lot. Center of mass, unstable equilibrium, rotational. I am now. I am certainly now. No, I think you oh, I do. No, I do. But I was just kind of flabbergasted about this. Now thinking about the physics of it, there's so much.
I don't even know if I do
I actually took a small video. You want to see it? I gotta go.
Someone? Really are on.
Yeah.
Well,
You got real.
Could you do it at all?
I don't think I can do even one.
The little caveat, his tire was flat when it wasn't supposed to be, so we did it on a flat tire.
Because that adds another physical.
So the spinning ball is on the inside. Yeah. Pretty well.
Maybe jot down a few things.
All right, folks, I did grade visits and posted the grades on Blackboard, so you can check that out. I'm not going to hand them back yet because there's still a couple people who haven't taken it yet. They were in sporting events, and they're taking it this afternoon. A few people did make it up already. I haven't graded those yet. We just finished. So I'll get those grades posted as soon as I can. If you do want to see what your grade was or why it is what it is, then come see me and we'll talk through it and answer any questions you've got as we go. Similarly, if the grade was good, awesome, good for you. There were some perfect papers, 20s out of 20, that's awesome, great job. There were some that were probably not as good as you wanted to be. Nobody was like, no zeros or anything like that. Everyone at least answered some, and I think that's a foundation we can build on. They say you can edit a bad paper, you can't edit a blank paper, so it's true. It's the first one. Now you guys know how I quiz. Now you have information. The quizzes, the tests are all structured about the same way. Tests are just longer versions of the quizzes. So better to miss points on this one than to miss points on the test, which is worth a lot more percentage-wise of the grade. So, of course, the first one's always the hardest. Just by default, because you don't know anything about it. You don't know about this class, you don't know about me. Now you do. So now you know if you didn't do as well as you wanted, we know how to prepare better next time. If you did do as well as you wanted, then do the same preparation or more next time, and you'll keep up the good stuff. Yeah? What's that? You're one of the people. I can't keep track. I got a lot of students. So, I think everything that I said to you is true. I don't tend to be a liar of things. I sometimes pretend, but I don't outright lie to you. Everything on the test was something you had seen one way or another. Either we talked about directly in class, I showed you directly in class, or was on the homework. Yeah, that's always going to be the case. It's never something out of the blue. Sometimes it's a novel application. Sometimes it's something that you're applying it in a way you haven't done before. But it's always something that you have done. It's never something that is just like vaguely referred to. Or I know sometimes professors will reach pretty far to get stuff. There's enough stuff that I don't have to reach very far to get. So it's not like out of some vague excerpt from the textbook. Although all the stuff that we did cover and all the stuff that we did test on is in the textbook. So if you need more clarification, that's a good reference. People don't use it, and I don't know why. Because it's free, you don't, like sometimes if it's not like expensive, people don't value it. But there's good information in there. It's all a lot. Any questions about that? I mean, I can't answer specific things because, like I said, there's people who haven't taken it yet. But time frames or anything like that? We're on to the next stuff today. We're going to be talking about, we are going to talk a little bit about fields, but that's from last week. We're going to start talking about potentials, which is coming up. Yeah, there we go, right there. That's that.
I have a question.
Okay.
Would it be possible to like reference, excuse me, the like slides while you're lecturing? Because like, I like to have
So,
things like written down.
Yeah, if you look at the syllabus, sorry, I didn't mean to interrupt you, but I got to get the thought out. If you look at the syllabus, it says what the lesson topic is for the day, and it says what part of the textbook it's from, and those slides they're from the textbook. Those pictures are copy and pasted from the textbook. I downloaded them from the textbook's website,
Okay,
and I look at them when I'm prepping the lessons,
okay.
right? So I won't be like citing my source as I go, because I can't, my memory's not that good,
That's fine.
but it's all listed. A good question. Okay. So, yeah.
Is it possible like in class to do more like hours?
We're going to start off with one. Just as you guys. No, we have nothing planned for a while. Also, just total side note, a couple people messaged me last night, kind of late. I was up because I was watching football, but at the same time, it's a little hard to respond to those questions so late. I'm tired too, so like, sometimes they're a little tricky to figure out what you did right and wrong. My advice is start early on those, so like, you can ask the questions earlier. I do try to get back to you every time, even if it is late, but my preference obviously is to do them early. And then I can find errors. Sometimes there's an error in the system, you know? Like, if it's 11 p.m. on a Sunday night, it's a little harder to fix that problem. So the sooner we find it, the better. Was the video helpful? The setup video? Yeah? Okay, cool. Okay, so let's get started. Last class we were talking about electric fields. I want to do a quick problem about electric fields and a certain type of fish in Africa that generates electric fields and uses electric fields to find its prey, which I thought was kind of cool. So you can read the problem. I'm not going to read it to you, but it's this odd fish. I looked up a picture of it a couple years ago when I first saw this problem. It's weird. It's got like a weird nose, hence the name elephant nose fish. It lives in the Congo River and generates an electric field that helps it find its prey. It can detect a change in electric field as small as 3 micronewtons per coulomb, micro being 10 to the minus 6. We want to know how much charge. And it lets us model it as a point charge, which is convenient. So we can use our point charge equation for electric fields. How much charge is needed to produce this much change in field. And we're given a distance in centimeters. We'll have to change that to meters too. So micro is 10 to the minus 6. Centi means 10 to the minus 2. So we get 3 times 10 to the minus 6 per coulomb for the electric field. We are given 0.875 meters for our distance. And it asks us how much charge. We're going to solve for charge. Do we have some sort of equation that associates those quantities? Charge, field, and distance? I see people nodding. Do you know an equation that associates those quantities? What's the relation? Specifically for a point charge. we have 3 equations to look at that we've covered in this class so far. That's not that many. Only one of them has those 3 quantities in it. Which one? Listen.
Q times Q over R.
That's it. R squared, but you got it.
R squared, yeah.
Yep. So electric field equals K times Q over R squared. E is the electric field. K is the constant. Q is the charge. And R is the distance. The distance is squared. It asks us to find the amount of charge, so we're going to have to do a little bit of algebra. We're going to have to manipulate the equation a little bit. If I'm solving this for Q, for the charge, what does that equation turn into? Do the algebra for me. I'm tired. It's the first class of the day. You guys are already warmed up. What is the, do the algebra, what's this equation going to look like? I heard somebody say something, I didn't.
Is it ER squared over K?
So you're going to multiply the R squared up, divide the K over, so Q equals E R squared over. You gotta be confident. Yeah, you are. Heck, yeah, you did. No, I'm complimenting you. Yeah, great. All right. We have all of them, don't we? We know what E is. We know what R is. We know what K is. Plug them in. Don't forget to square your R. Don't forget that it's 0.875, not 87.5. You got an answer for me? You might as well say it.
2.58 e to the negative 16.
Awesome. So I got 2.55 times 10 to the minus 16th, but that's probably just rounding in the middle somewhere. So we have a total charge, Q, equals 2.55, or something in that vicinity, times 10 to the minus 16th. Almost. If that's not what you got, you probably plugged something in wrong. That's why we're doing this practice. Now, this is just a pet peeve of mine. If you wrote 2.5 and then the letter E and then minus 16, I know that's what the calculator spits out, and I do know what it means. Like, I'm smart enough to figure that out. So I didn't take any points off for that, but I like seeing it written times 10 to the minus 16th because it's a little bit more, we'll say, mathematically sound, because those exponents, we can use them to our advantage later. So we want to put them in the form that's easiest to use. So that's just my own personal preference. If you do put the E, I'll probably not care, but my advice and my preference is that you write out the times 10 to the thing.
No.
Okay? So if you did do the E, you wrote the E on your test, you weren't alone. A lot of people did that. I don't like it. So I didn't take any points off for it. No, it didn't hurt you. It just, it'll help you long run to write it down. Yeah?
I don't know if you make the questions on the homework or you have
I do not.
control to change them. Okay, if we have to use exponents in the future, like for more stuff, how's that gonna work with homework? Because it forces us to write E.
That's fine. I don't check. It automatically checks those. Write it how it wants it. When you're doing the quiz and the test, write it how I want. think about who's assessing. Fair enough?
Yeah.
They mean the same thing, right? Just that's how you write it in math class. The E is how you write it on your calculus.
I didn't know if you were able to like change.
I'm not. At least, maybe I am, but I don't know how to, because it's a new system. It's a computer. It's essentially a calculator, right? That's how the calculator likes it. I'm not. I can pick out which pictures have bicycles and crosswalks and all, no robot. That's funny.
I thought it was a good one.
All right, thanks. We're not done quite yet. I just wanted to give everyone a chance to finish and make sure they got the right answer. But we're not quite done. It asks another thing. It says how many electrons are required to make that much charge. How do we go about finding how many electrons are required to make that much charge? Well, we know how much charge there is total, and we know how much each electron carries when you take an electron away or give an electron to something. That's how much charge the electron either adds or takes away by its movement. So if we know the total amount, and we know how much each individual has, we can use that kind of like a conversion factor. The same exact process that we use for converting units, we can use to figure out the number of electrons. So we know how many coulombs we have. We want to know how many electrons that would give us, and we know the number of coulombs per electron. So if we have 2.55 times 10 to the minus 16 coulombs, and we know that one electron has 1.6 times 10 to the minus 19 coulombs of charge. The coulombs cancel out. We're left with electrons as our label there, our tag, our unit. So we take this number, divide by that number. This is why that whole writing out the 10 to the minus is so convenient, because the 10 to the minus 16 and the 10 to the minus 19, we can just look at that and get an idea of how big it's going to be. And what do you get for an answer? You gotta say it loud, I can't hear you.
1,596.
I got 1,595, but those are close enough that it's just a rounding issue, and I would give you 100% credit for that. So, nice. Good job. Own that. Don't be hesitant, don't be quiet, say it loud and proud. One more time, 1593 point something. So we'll round that up because you can't have part of an electron. I mean, there are quarks which are like, you can take a proton and break it apart, because it's made out of quarks. But we don't need to talk about quantum mechanics in here. That's a little deeper than we want to go. Okay, so probably plugging something in wrong. Let's maybe stop by office hours and we'll practice a few of them. Sound good? You know where you need to get to, and if you're not getting there, we'll find out why. Other questions? If I asked you a question like that on the test, you'd be able to do it? Good. I'm glad to hear it. If I have a positive charge over here, and I go to exit screen right, and I grab myself a positive charge, and I drag it. And I pull it all the way over here. It would require some force for me to do that, right? I have to move that thing through a distance by applying a force to it. I apply a force to move it through a distance, and then if I let it go, what's it going to do? It shoots back over that way, right? Because I applied a force and moved it through a distance and placed it in some place where it had the potential to move, right? So when I let it go, it does move. Have you ever seen that before in a physics class in your lifetime? Last semester? Week before? Yeah, you've seen a similar situation?
There was like a car set up or something, electron flying.
Like a spring effect.
Oh, okay. Yeah, okay, all right. So with a spring, when I coil the spring, I'm pushing a force to move something through a distance, and then it has the potential to move, right? Any other places you've seen that? That's a good one. That was the second one I was going to go to. You jumped right to the second one. You know, where you apply a force to a thing and move it through some distance, and then it has the potential that when you let it go, it starts to move. Oh, who said that? Nice. So I keep using terms here, and I'm doing them very purposefully. I don't know if you've noticed that. You apply a force to move something through a distance. What's that called? Physics 1? Doing work, right? You're doing work. What is work? It's moving a force to move something through a distance. But what else is it? What? That's force. Force is MA. That's the second law. I know, Physics 1, long time ago. Like a semester ago.
FD cos theta.
A year and a half ago, but you had a really good teacher.
Yeah.
Not that these
You
guys
said
did.
it right here.
Is
What?
it FD cos theta?
It is absolutely that thing. It also equals something else. You're right, but there's another thing that it equals. When I do work, what do I do to the system, I guess? Maybe I do accelerate it, because when I push it, I'm applying a force that causes it to accelerate. By accelerating it, I give it something. I give it energy, yes, oh my gosh.
Year and a half later. Yeah.
I mean, I'm not
remember.
comparing myself to Dr. Jones, because Dr. Jones is amazing, and if I did that, I would lose that competition. But that being said, she was my student, Physics 1. So, it was a long time ago, I know, I was fishing for that, but you got that, like, as a group, you got that. It is FD cosine theta, it also equals the change in energy of the system. So, when I do work on a system, I give it some energy. That was true when I lifted up the object. By lifting it up, I multiply the force that I applied times the distance through which I lift it, and that gives me the total energy that I've given it. The total work done equals the total energy I've given to that system. Does this ring a bell at all? Okay, good. Ringing a bell is doing work and putting sound energy in the system, so nice. Because the force that I'm applying is the force against the force of gravity, mg, and the distance it's moving is h, mgh. That's a type of energy. What does mgh equal? Potential energy. Specifically, it equals gravitational potential energy, because you said gravity. It's the gravitational potential energy that I give the system. Is this coming back to you a little bit? I'm saying a lot of words. I'm saying them fast because you spent a whole unit last semester doing it, or several semesters ago. Some people it's been a while, but it's kind of coming back a little bit. When I apply a force to move something through a distance, I do work. Work is FD cosine theta because we care about the parallel lines. It also equals the change in energy. So when that happens, I'm giving energy to the system. If I'm lifting it up, I'm giving energy to the system. If I'm compressing the spring, I'm giving energy to the system. Energy isn't created or destroyed, it just moves around. So like I convert some of my breakfast food into mechanical energy, which converts into the potential energy of the system that I pushed. The electron or the proton that I just described on the board, where I pulled it off screen and pulled it from some distant spot far away and brought it nearer and nearer and nearer to the other charged particle, that's giving it energy. In particular, it's giving it a specific type of energy, and it's identical in concept to the potential energy we gave it before. Be it a spring, be it gravitational energy, it's the same kind of deal. So we're giving it potential energy, just like we were giving those other things potential energy before. But it's a different kind of potential energy, it's electrical potential energy. Now you can write that lots of different ways. If you're like me and you're like a 14-year-old trapped in an adult's body, you can write it as potential energy, subscript, electrical. Because then you write P on the board, and go to one side, like a middle school kid. You'll never forget it now. I know it's silly, but I say silly things so that you remember this stuff. You could write it as electrical potential energy. I don't remember the subscript. I don't remember the symbol that your book uses. It really doesn't matter. makes no difference to me. This concept is foundational. We don't actually use it a lot, but we can figure out a lot of other stuff based on this. The stuff we're going to cover today is very poorly named, which can cause some confusion. We're going to talk about 3 very different concepts that are related to each other and have almost identical names. It's super frustrating because it's easy to mix them up. What we're talking about now is electrical potential energy. It's a type of potential energy that can be converted into other kinds of energy, just like all of the energy you've studied forever. But it's not the most useful concept. It leads to more useful concepts. Specifically, it leads to a concept called electric potential. And those sound like the same thing. I didn't name them, I promise you I didn't name them. I would name them something different. But electric potential is a different thing, but it's related to this thing. So it's super easy to get them mixed up. So I'm going to be as careful as I can with my words, and I'm just giving you a heads up that it's easy to get these things mixed and matched. Now, electric potential is super useful within confines of certain contexts, but there's a more useful way to look at it. A more useful version of it, it's called potential difference. Potential difference. Electric potential energy, then electric potential, and then potential difference are all related quantities. We're talking about all 3 today. They're not the same, but they're related to each other. You use one to get the others, and it's super obnoxious that they don't give them better names. Those are our 3 big ideas for the day. Once we get through those, we'll just do some practice problems. All right, when I drew that charge in from far away, if it was very, very, very far away, the interaction between the 2 charges is very, very, very weak, because we know Coulomb's law says that the distance between them squared. We're dividing by that amount. The farther you get away, the weaker the force is going to be. If the weaker the force is, the less influence it has and the less work you do in moving it. So, as such, we look at the 0 point for our energy, in this case the electric potential energy, as being infinitely far away. If it's so far away that the force is essentially nothing, then the work that it takes to move it closer is really small. But the closer and closer and closer you get, the more and more and more force those 2 things apply on each other. And the more force it's going to feel, the more force it takes to push it into that spot. So therefore, the more work you have to do, and the more energy it has. So if I push them really close, it's going to have a lot of potential energy, because it's going to get shot off really fast. The farther away you are, the less potential energy. So we do have an equation for the electric potential energy of a point charge, like this one. And it looks like this. I'll just have it. Switch tabs. The electric potential energy is going to equal the work done, which equals the force times the distance times the cosine of theta, but we're going to idealize this and we're going to say we're bringing it straight in. So the angle is going to be either 0 or 180, so we're going to multiply by 1. So that cosine theta term drops out, and if force is K Q over R squared, and D is the distance between them, D is the distance that's moved, and that's going to be the distance between the 2 charges, that would be R. So F times D would be K QQ over R squared, and we're multiplying it by the distance R. What do we have left? We have 1 over R squared multiplied by R. Close, you're thinking about it right, but I didn't describe it right. Q, oh, that's Q over R squared times R. What? That? KQQ over R. You gave me the worst look.
What?
When I was describing that, like the math, and I said, okay, so what's left? You gave me a look like, what's wrong with you? I actually like it when people do that, because that tells me if I was clear or not. If you just sit there with the poker face, I don't know if I made sense or if it was nonsense, so at least that's informational. Okay, so what's left? KQQ over R. K being the Coulomb constant, Q and Q being the two charges, one being the point charge and the other being the point charge that I'm pulling in. And R is the distance apart there. In the old homework system, it asked us to find out how much work was done in creating an array of charges. Remember, we kind of made a square with charges and we put a charge in the middle. It took work to put those charges in that spot. Like, we had one, we just put it there. That's easy because there's no outside charges. But to bring another positive charge in took work to do. To bring another positive charge took other work to do. And you can calculate that fairly easily by just summing them up. How much work did it take to bring one in? How much work did it take to bring the second one in? You just use this equation and you just do it over and over again. KQ over R. R being the distance away. Bless you. Good question. Right. All right. As with all energies, it's measured in joules in our class. There are other units, but that's the one we use in physics class. And we can try it. We can say how much work is done to bring. Let's just put some numbers in. Make sure we get some practice together. Where are my athletes in the room? Do you have a number associated with your athletics?
I can go and
No. And then another athlete in the room that has a number? You have a number?
Of what?
That you wear?
Oh, 53.
53.
It's a ball.
And a final number?
16.
I could ask this question two different ways. And both ways are the exact same question, but they sound a little different. So you can jot it down both ways if you'd like. I could say, how much work is done in putting these charges in this configuration? I could also say, what?
Yeah.
I was flapping you with my nose on behalf of that.
I'm sorry.
Why
I
are you
want to
sorry?
make sure that.
Do it right. I'm teasing you, obviously.
I know. I'm scared.
You didn't do anything wrong, and you shouldn't be scared. You good? All jokes aside, ask